In this video, I want to start talking about question 6 on the midterm. So what's going on here? Well, so this is the data set that you get. You just get, n integers. You're also given that those integers come from two Poisson distributions. So let's start with just making up some integers and figuring out what does it mean for them to come from two Poisson distributions. So this is the set. And if you know about the Poisson distribution, you don't even need to know much other than to say that, it has this parameter lambda, and as is given on the midterm, the lambda is basically, the long-term average of the samples from that distribution, right? So if those numbers are coming from two different Poisson distributions, you would figure, okay, so those two probably come from the distribution with a large mean, and then the other ones are coming from a distribution with a small mean, okay? So the way this is generated is you're saying, well, generate the first sample from one of the two distributions, the second sample from one of the two distributions, and so on, and probably those were generated from the second larger distribution. So let's write down the algorithm for actually generating this data set the same way we did for the mixture of Gaussians, right? So you would say, okay, so the first thing that you're going to do is you're going to pick lambda 1 with probability pi 1. And I'm just kind of saying, okay, this probability is going to be called pi 1, and lambda 2 with probability pi 2. Well, you know that pi 1 and pi 2 got to add up to 1, so you could say, well, this is just pi, and this is 1 minus pi, whatever works. So once you did that, and let's call this, one of those. So let's call this kind of lambda prime. And now what you can say is, okay, so generate k from Poisson lambda prime. Okay, that's the whole process. So pick one and then generate the k from here, from the Poisson distribution. Pick one of the lambdas, generate the k, and so on. Okay, so let's make up some plausible looking numbers. So here you have fewer large numbers than you have small numbers. So maybe you would say, okay, so maybe lambda 1 is equal to something, maybe 1.5, and maybe lambda 2, so here it's easy, just take the average, is equal to 49. And so there's fewer of those, so you would say maybe pi 1 is pretty large, maybe it's 0.8, and maybe pi 2, here you have to say 1 minus 0.8, so 0.2. Okay, so here what's going on clearly is here you picked lambda 2, that was a low probability event, but it happened, and then you generated a 50 from this Poisson distribution. Okay, so anyway, what's the answer to the first part of the question? Well, the answer is, well, those are the parameters of the model. They completely specify how to generate random numbers from this model. Okay, so the next question is, well, you observe this, and you're assuming that you know the lambda and the pi, and you want to know what's the likelihood of the data. So what you want to know is, if those are really other parameters, how likely are you to see this kind of data set? And we pick the numbers such that the answer is, well, pretty likely that could happen, right? If we picked some other numbers, so if this was 15 million and this was 30 billion, then this would be an extremely implausible data set for those parameters. Okay. So what is the likelihood? So in other words, what we're asking is, what's the probability of all the k's given lambda and pi? And we can just rewrite it as the product of the probabilities of the individual k's. So this one and this one and this one, given lambda and pi. And here we have a problem because, well, you don't know what exactly is the probability of ki under lambda and pi because you don't know whether ki came from this distribution or from this distribution. So the way we solve it is by, like we did in the mixture of Gaussians example, by making up a new variable. So we'll call it zi, and zi is going to be 1 if ki is from Poissons lambda 1, and it's going to be 2 if it's from Poissons lambda 2. So we don't know what zi is because all we know is the case, but we know it exists because we know we're assuming rather that k is coming from one or the other Poisson distribution. So okay, how does this help us? Well, this helps us because now we can say, okay, so the probability of ki given lambda and pi, well, that's just the sum over the possible zi's, so the sum over zi in 1, 2 of the probability of ki and zi together given lambda and pi. So you get to do this, right? So you get to say, this is just a side note, the probability of A is equal to the sum over all the possible B's of the probability of A and B together. Okay, you get to say this. So alright, so now that we've said this, why does this help? Well, this helps because now we get to condition on that zi and then multiply back by its probability. So that's going to be, again, the sum over zi of 1, 2. But now what we're going to do is we're going to say, okay, so this is going to be the probability of ki conditioned on zi and also lambda and pi times the probability of zi conditioned on, again, lambda and pi. Got to do this. So we conditioned on zi and then we multiplied back by zi. The lambda and pi were fixed throughout, so it's okay. Alright? Why did we do all that? Well, because now we have, well, what's the probability of observing ki if the assignment was zi and those are the parameters? That's easy. That's just the density, right? So let's write the first term. So again, we have this sum over the possible zi's. But here we'll say, okay, so this is just the density. So this is just p lambda zi. So this is going to be either lambda 1 or lambda 2 of ki. So this we just plug into the formula, into the probability mass function of the Poisson distribution, and we'll get it, okay? We didn't really care about the pi, we didn't use it because if you know what the zi is, you don't care what the probability was for, you know, lambda 1 or lambda 2 being picked because it was already picked. The zi specifies it. So now we need to multiply by the probability of zi given lambda and pi. So what's the probability that zi equals 1? Well, it's pi 1. That's what we said. What's the probability of zi being equal to 2? It's pi 2. We don't care about the lambda at this point. So this would be times pi zi. Okay? And we're done. So the probability of k is this product of the probabilities of the individual k's. And then this is the probability of an individual k. So that gives you the likelihood of the data if you don't assume that you know the assignments, and usually you would not. And again, what does this thing measure? So what does this thing measure? Well, it measures if lambda 1, lambda 2, pi 1, pi 2 are fixed, how likely is this data set to be generated? And again, so kind of for those, what would be an unlikely data set? Well, one example would be, let's say the lambdas are okay, but the pi's are wrong, right? So let's say that, the data set looks kind of like this, so like 51, maybe like 40, and then maybe here's a 1, and now it's again 49 and 52, and so on. This is, well, say that this is done. So under those parameters, this is looking kind of unlikely, right? Because most of those numbers seem to be coming from Poisson lambda 2, not from Poisson lambda 1. It's not going to be terribly unlikely. It could happen, but it's less likely than, observing something where the proportions are correct.